So the average was a 71 before bonus, a 74 after bonus. But as you guys saw, there were 2 people that ended up with C's in the class on the exam, which means that is not representative of how the class did. We actually have like a U-shaped distribution. We had a lot of people with A's and B's, a lot of people with D's and below. And the bonus points disproportionately helped people that scored higher on the exam. So your midterm exam analysis will disproportionately help people that did worse on the exam and help you bring your scores higher, not just to get a higher grade, but to prepare you for the final. Because if you miss those concepts on the midterm, how likely are you to miss them in a few weeks when we have the final? Pretty high. So I need you to identify what you did wrong, master it, so that you can answer it correctly on the final. So in your midterm exam analysis, you will be analyzing the questions you got wrong and submitting 3 things about them. I can never spell answer. You need to provide the correct answer, which will not be hard because I'm going to upload the key. I'll put it right in the midterm module, which means your challenge is not just to identify what the correct answer is, but to rationalize why that is the correct answer, or explain why your answer was wrong. Maybe do both. Why is the correct answer correct? Why is your answer incorrect? For instance, if you are going through that resonance one that we talked about, and you might say, the correct answer is A, B, C because oxygen and nitrogen have full octets. I misunderstood that they had full octets, so I placed them as underneath on appropriate charge placement, right? 2, why was it here? What I would do if I were you is look through my learning objective documents that are at the top of each module and use that as a rationalization of why those questions were on the exam. We had a question on resonance because we were told that we would rank resonance forms. That's pretty good. Ultimately, that will get you to dig into the learning objectives a little bit more and look at those named items to help you kind of register them better for the next time. And then, why did you miss it? Sometimes I get just like copy paste answers here, and that's because sometimes the reason you missed it is the same. I did not study this. I misread the question. I was expecting that the question was asking something else. Easy. This is your self-reflection. I don't want you to be mean to yourself here. I want you to be critical so that you can identify those pitfalls before they happen again on the final. But I don't want you to tear yourself apart here and just say, I'm really bad at this. This isn't my strong suit. I'm never going to understand this. That's not helpful to anybody. The whole point of this is to identify where you misstepped so that the next time you don't have that misstep. You can earn up to half of the points that you missed, which means for multiple choice questions, great, you get 1 of 2 points back. That's easy for me to do. But for short answer, like the nomenclature, the arrow pushing, the ranking, I need you to upload a picture of your question or pictures of your exam, because I need to know how many points you missed in order to know how many points you can get back. In the past, students have forgotten to do that, and I'll still give feedback. The thing is, you don't earn half of your points back for turning this in. That's why I say you can earn up to half your points. You earn your points back for correctly identifying the correct answer, explaining why it's the correct answer, why yours is incorrect, why it was on the exam, why you didn't get it there, having that self-reflection. Without having all of those and without having them correct, I don't give points back. I'm giving you points here for showing that you are learning it in this analysis. If you ask students that have had me in the past, they'll say that I do go through each line, each question, and I report how many points you're earning back for it. And if I don't give you points back, I say why. This is a one chance assignment though. I'm not gonna give you too many chances to earn points back on these because there needs to be some skin in the game, right? There's got to be a stake to not getting it. So for those of you, I think, did I already close that? For example, someone here with a 50 missed 20 points, they can earn up to 10 points back. That can take them from a 50 to a 60, which is what, a C to a high B. It's pretty good. A low C to a high B. So if you did poorly on this exam, this assignment is for you specifically to boost your grade, to give you confidence in your understanding, to help you master these concepts. I might end up grading these closer to the final. It kind of depends on when I have time to grade them and when they get turned in. Oh, I keep forgetting to say this. You can write a little analysis of the bonus points, but you can't earn the bonus points back. So I'm happy to like give you feedback on your understanding of the bonus points, but this is just to earn credit back for the graded questions. For formatting, I keep forgetting to just take a screenshot of somebody that's done this well and put it on here. There's a few ways that I would recommend doing this. If you need to turn in some of the handwritten stuff, then you're probably going to want to do that on a separate piece of paper and just take a picture of that as well. So I might recommend having a Word document. Take a picture of the question or questions you've missed and put it into the Word document, and then have your analysis of the question beneath it, and then the next question and your analysis, and the next question and your analysis. And if you're doing that for some of the written work, the analysis, of course, is going to include your new written work showing you the answer. This is something that I think maybe I need to figure out how to say it in here. For written work, I'm going to upload this exam, right? So I've had students in the past that just take my answer key and take a little screenshot of the correct answer for the arrow pushing, and then they say, this is what the correct answer should be. Yes, it is. I hope. I need to see that you can do it. A lot of the multiple choice stuff, I know that you can circle it. You circled the wrong answer, so I know you can circle the right answer. But for the written work, I need to see that you can do the written work. So I want to see your written work, not my written work. Does that make sense? And without the questions, without knowing how many points you lost, I'm happy to give feedback and say, yes, you've correctly understood what you did wrong. You've corrected it. But I don't know how many points you lost, so I can't give you any points back. And then I've often had students that just send me pictures of their exams after that, hungry for the points. So take advantage of this. Start early. Do it over the next few weeks if you want to. The deadline for turning this in, I've set this as April 23rd, which is right before the last week of classes. And the last week of classes is going to be review for us anyways. We're going to have 2 days of review. So that's when I've asked for you to turn it in, but the hard deadline, like the last chance I'll take it and still give you points back, is when you come in to sit down for the final exam. Doesn't make any sense for you to take the final exam and then go back and do the midterm analysis and try to get more points. Just doesn't make sense. This is in preparation for the final. Okay. So if you're not happy with your grade, what should you do? Midterm analysis. Questions? Yeah, Carla? Thanks for asking. It's actually easier for me if it's question by question. But I understand it's easier for you probably to just attach it all at once at the end. That works great for me. If you crop the image and just keep cropping it for the question that you're answering, that works great for me because then I can see what the question was, the points you got, what you got wrong, and see your thinking without having to go back and forth between them. Thank you. Annie? Yeah. If you're working on your iPad and you just want to draw everything, that works for me. I really don't need to see a screenshot of the exam. So if you say this is how many points you lost out of it, I'll usually accept that as well. Allie? Yeah, the 23rd. That 23rd deadline is more for you than it is for me. I guess it's partly for me too, because on Friday, the 24th, then I can try to sit down and grade as many of them as I can. That way, going into the review week, you know already if you've mastered those concepts from the midterm or not. But you could turn it in anytime before we get to our exam on the 4th, May 4th. You're welcome. Okay. Now we get into the heart of it. The real stuff. I try to remind myself when I build material early on in the semester that everything that I'm trying to teach you in the first half of the semester is in preparation for the second half of the semester. From here, we're going to be talking about reactions. We're going to learn a lot of reagents. We're going to understand how to convert one functional group into another. Thanks, Calvin. I've had a lot of students say that this is when it gets real. And we're going to apply all of the stuff that we've talked about in this half. So this section 6 is meant to be kind of an overview. We're going to look at a lot of different examples of chemical reactions. We're going to talk about terminology, facets of how this works. In section 7, we're actually going to take a little step back from reactions to focus on alkenes. We're going to talk a little bit more about how alkenes work, what they do. And then section 8, we're going to go through alkene addition reactions. Alkenes have a lot of different reactions. So introing alkenes as a functional group is a great way for us to segue into a bunch of different chemical reactions. Just to point out, oh yeah, this is actually wrong. I have on here that Friday is the last day to withdraw, but I think it's now actually March 24th. So a week from tomorrow is the last day to withdraw. That's just an important tuition deadline. Well, actually, you don't get tuition back, but transcript deadline. If you want to withdraw, that's the last day before it shows up on your transcript. Sorry, it will show up with a W. God, it's like I don't know what I'm talking about. Also, a heads up, next week I am out of town. And I keep forgetting to tell you guys this. So we're going to be having Zoom lectures. I will send you guys the Zoom link before class Monday and Wednesday. I'll be at the American Chemical Society conference in Georgia. Is anybody here going to that? No, there are just students scattered all across our clubs that are going with research projects. So I'll be meeting with you guys over Zoom. As usual, it's not required that you're on Zoom, and I will do my best to record it. I'm not sure how this recording is going to work, though. I don't think that I can upload it. No, just kidding. I think I figured out. I can download a Zoom recording as like a file, and I'll upload that file to YouTube. So I should still be able to upload it to YouTube. That's going to kind of overlap with us talking about alkenes and getting into alkene addition reactions. So it's not like the most interesting lectures anyways, but I'm going to try to still have worksheets that we can collaborate on over Zoom. It's going to be an interesting run, so I appreciate your guys' help with making it interesting. Both Monday and Wednesday. Then after 3 weeks of this new unit, we've got our unit test. We've got another 3 weeks before our final unit test, 2 weeks of review. It's just an avalanche at the end of the semester. But the good news is that sun is not going to set until after we leave class. So you guys will at least feel awake every day in here, I hope. All right. Section 6. Organic reactions. There are 3 major types of reactions. And don't go back and watch my old video because I might call it a class of reaction. I don't think that there's like solid terminology on this. And the distinction between type and class here is incredibly vague. We're just saying ways to group reactions. The first major way that we will identify a reaction is addition. Addition reactions consume a pi bond and add 2 new groups across that pi bond. And of course, these 2 new groups don't need to be 2 atoms. They can be groups of atoms. They can look like entirely other molecules, but it's just that we take the 2 atoms of a pi bond and we add across it. We'll be dealing in this semester a lot with carbon-carbon bonds. So to give a generic example here, this is the addition of AB across what functional group? Alkene. We'll also be talking about carbon-carbon triple bonds. How many pi bonds in the alkyne? So how many sets of addition can I do? 2. And we will oftentimes abbreviate if we're doing multiple equivalences. We will say that we're doing 1 equivalence or 2 equivalents. Or if we're doing 2 equivalents, we might say that we're just adding this new reagent in excess. But again, this just allows us to do addition more than once. So here I haven't just added 2 new groups, I've added 2 new groups twice. by consuming 2 pi bonds. In OChem 2, you'll add across more than just carbon-carbon pi bonds, carbon-oxygen, carbon-nitrogen. Great question. Why is it not an alkene product instead? This actually gets into the idea of reaction intermediates, which is one equivalence of AB does add to form an alkene. And then, just like the alkene reacts, a second equivalence of AB adds across that alkene to give us something more alkane looking. Or can I say the SP goes to an sp2 intermediate, which then reacts just like we saw sp2 intermediates already react. Did you raise your hand? I thought I saw a hand up here too. Did I answer your question? Great. This is not really in any particular order. I like to go alphabetical, but the opposite of an addition reaction, right, an elimination reaction. Isn't that terrible? They had the chance to call that a subtraction reaction, which has a really nice flow, and they called it elimination instead. Instead of adding 2 new groups, we will remove 2 new groups and create a pi bond. What are these groups that are being removed? A lot of times one of them is a hydrogen, and another one, we'll see a lot of elimination reactions with halogens, alcohols. In fact, you guys will be doing all of these reaction types in your lab class as well. You'll get a chance to dive into each one. If we were to generalize the elimination reaction, it is essentially the exact opposite here. However you'd like to abbreviate those groups is totally up to you. I'm going to stick with that A and B. And depending on the number of A and B groups that you have, dictates how many eliminations you can do. Sometimes I like to mention pitfalls that students have pointed out before, but then sometimes when I do, it just opens confusion that wasn't going to be there before. I have students that look at elimination reactions and tell themselves, I have added an alkene to my structure. I've taken a molecule and that didn't have an alkene, and now I have an alkene. So it looks like I've added a functional group, which is understandable. But the idea is not adding functional groups at all. The focus is totally on pi bonds. Elimination reactions remove groups, which allows for that pi bond to form. We had a question on unsaturation on the midterm that was had quite a few people miss it. What does unsaturation tell us? Pi bonds and rings. And why do we call it unsaturation? Could have been bonded to something else. Like here, my atoms can be bonded to A and B, or they can be bonded back to themselves. So we could really call this like an unsaturation reaction, because I will unsaturate the molecule. That's the idea. I'm eliminating groups, so I should increase my degrees of unsaturation. Addition would be the opposite. This is a saturation reaction. I'm taking places where I don't have a lot of groups and I'm adding them there. All right, my last reaction type is substitution. Sorry, I want to point out this little abbreviation I'm using. You guys okay with that abbreviation for reaction? RXN. The substitution reaction, I mean, pretty straightforward. One group leaves, one group joins. If I've got this carbon bonded to a B atom, well, how about an A? And I introduce a new reagent, I can substitute A for B. These are incredibly generic, right? Like the most generic they can be. So I want you guys to use these reactions on the top half of your sheet. And I want you to label them with A, E, or S. Or if you want to, addition, elimination, substitution. But I want you to go through each reaction on this page and label it with the type of reaction that you see. Oh, I didn't upload it to Canvas. So if you'd like that, I will do that right now. Oh, you know what it is, but that's the old version. Yeah, that's because I improved it. That's the new version seems like it's populated. Please.
If you trying to say this in a way that would make sense. If you're like either one, elimination or addition, if you have an alkyne, would it ever stop at an alkene? Or
Yeah.
It would.
You've got one in front of you, actually. Do you see it?
Oh, this one, right?
Yeah.
Okay.
Alkyne to alkene. We're gonna learn our reactions kind of by functional group.
Okay.
So we'll have a unit or a section on alkynes, and we'll talk about how to take the alkyne and stop at an alkene, or how to take the alkyne and from the alkene that it forms continue further past the alkene. We're going to start with the alkenes. So moving to alkynes later really just means I have like a new starting point from alkyne now to an alkene.
Okay. Thank you.
Mm-hmm. Get them all? Great. Yeah. Oh, sorry, I didn't see them over there. Yeah, you want to do these three too?
Oh, these-
Yeah. Great work. Easy work, Colin. How about this one?
And if you're eliminating or if you're adding, because I feel like third in the core, but you also the bombs are weird now. Like
Mm.
you have this, but I guess you did just eliminate this and add something else, right? So is it both?
Because I added an alkene.
So you did add, even though you eliminated something. You just added.
Right, that's the
Okay.
confusion is it looks like I've added an alkene, but I haven't added an alkene. I have formed a pi bond. And we say that elimination reactions form pi bonds. So if an elimination reaction removes two things, yeah, one of them is the chlorine, that's obvious. What's the other thing? Well, the pi bond formed as the result of two things leaving. One thing that left was chlorine. What was the other thing? Do you see how it went from 3 CH3s to 2 CH3s and a CH2? I agree with you that the bonds are wonky, but there's not really a better way to show that structure. So I would say it's more important to identify where the atoms are. You found that tertiary carbon and you mapped it to the product. You said that carbon is the same. Any of these three methyl groups can be those two remaining methyl groups. So then the third methyl group must be losing a hydrogen. Yeah. First, second.
Oh, okay. So this is like the first thing that's.
It's like if you go in the lab, you're not going to mix all of those at once.
Okay.
First, you're going to mix in the borane, let it react, and then at some time later, you'll mix in the basic aqueous hydrogen peroxide, and that will react with what formed in the first reaction.
Oh, okay. So this is like everything after all that's been done.
That's right. Yep. Good, good, good. No. How is the pi bond involved? Are we consuming a pi bond or are we creating a pi bond? Right. So
Oh, okay. Addition.
I've added a BR on one side of the pi bond.
That makes sense.
Good.
Ah,
How about this one?
wrong.
Yep.
This was elimination.
And this one?
This one's addition.
Good.
I think I got confused.
Okay.
But I think I got it.
Good. Yep.
Would that be substitution or addition? Are we adding hydrogen onto that?
Yep.
That would be addition.
That's addition.
So
Mm-hmm.
then that would just be elimination of that H to form the carbon.
An H on the O and an H on the carbon.
Correct.
Yeah, two groups left.
Yeah.
Good.
And then this one. So we removed the H. I guess we opened that up to form the cyclic compound and added the bromine. Would that be substitution? Or what?
Well, nothing's actually substituted. There's no group that. Okay, actually, I see what you mean. The oxygen has substituted its hydrogen. That's fair. But we also consume a pi bond.
Yeah.
So maybe it's not as simple as just one. Maybe it's a bit of a mixture.
Okay. So is this like where there's two BRs, one of them takes the hydrogen?
It's not as simple as that.
Okay.
But that arrow's going the wrong way for sure.
Oh.
If you use an arrow to show where a hydrogen should go, it means you're not using an arrow to show how electrons are moving, which is what the arrows are for. They're for electron movement. We'll look at that mechanism. So this is what we call a halo ether product. It has a halogen and an ether, and we'll look at that mechanism. It actually involves Br2 reacting with the alkene and forming a three-membered ring before the alcohol opens that ring, and then the other bromine takes the hydrogen from the O then. It's a little bit involved. 3 steps.
So this one is just
That's what I was looking for, yeah. But it's not bad to point out that some reactions don't seem to be as simple as just this or that. They're not always clear cut. Any answers I can question?
There's this being added or whatever's going on here.
Yeah.
But it's not over here.
Yeah.
It's gone.
Mm-hmm. Isn't that cool?
That's so rude. I don't think it's cool.
Magnesium canceled out the
Yeah,
bromine.
these.
Yeah. They left. You know what? Actually, that's a bad reaction anyways. That should have a 1-2 as well. It should be first magnesium, second H3O plus. But the magnesium does change the way carbon and bromine interact. And because of that reaction, the carbon changes its reactivity and it reacts with the carbonyl. But it's after that where the acid then protonates everything. But unfortunately, you won't learn that reaction until OChem 2. This is my teaser to come join me in OChem 2. Yes, 8 a.m. I don't think it's been scheduled yet. It could be Natalie Delmain. It could be Larry Grant. There's no decision on that yet. Yeah. I don't recommend it, but people do it all the time. Some programs will say that it's allowed. The U will teach alcohol chemistry at the end of OChem 1. We teach alcohol chemistry during OChem 2. And alcohol chemistry is connected with carbonyl chemistry. And carbonyl chemistry is fundamental to biochemistry. So I guess like depending on what's in your curriculum for OChem 1, it could be okay. I wouldn't recommend it. I would recommend finishing OChem 2 and then going into biochem. It's not impossible though. But OChem 2 is where you really nail down mechanisms. We're gonna start learning mechanisms here. You're gonna learn a lot more mechanisms in OChem 2. My students say when they get into biochem, the mechanisms from OChem 2 are just a lot of what they see in biochem. You know what? In terms of class time, we get the same amount of hours in class learning. Almost. It's like short by a lecture period or two. We get almost the same amount of time learning. You just have to do more learning per week and learn in a shorter number of weeks. So for my job is easy. I get paid for the same amount of time over a shorter period. As the student, it's a little harder because you're just pounded with information faster. It's definitely doable. For 50 minutes. A lot of times those four-year institutions have 3 hours of lecture and 1 hour of discussion or recitation. So that's just kind of built into our time here. But usually recitation is not extra material, it's just practice. And that's what I'm trying to do here is integrate all of that. You're right. Well, and you do if I have anything to say about it. All right. You guys want to take a break? Oh, okay.
I feel like we have some music.
Then let me do this. Let me talk about the other way that we look at reactions, and I'm going to have you consider these same things, and then you can kind of apply that and take your break at the same time. So I say that these are the reaction types, but as it turns out, some people would take the sheet that I've handed you and they would say, I'd never in my life call that an addition reaction. I'd call that a reduction reaction. I'd never call that elimination. I'd call that oxidation. There's some overlap between things that we refer to. And I want you to kind of have the understanding that these terms can apply to a lot of different things. And then when you get to those things, you can learn what term is more commonly used. So very broad base reaction types. I actually skipped over one, which are rearrangement reactions. But another way to consider reactions we can call reactions oxidation. I will say This is from the perspective of carbon. So we generally are not paying attention to whether oxygen atoms are being oxidized or reduced, bromine atoms are being oxidized or reduced. We're paying attention strictly to the carbon atoms. Sometimes we have to pay attention to just one carbon atom, and we decide whether it's been oxidized or reduced. Sometimes we pay attention to more than one carbon atom, and perhaps one is oxidized and one is reduced, and so overall, the reaction is neither oxidation nor reduction. An oxidation reaction will increase bonds to more electronegative atoms. There's not like a great way to show this as a generic reaction, but I do want to point out alcohols are things that are very commonly oxidized. And when chemists show oxidation over a reaction arrow, there are so many different reagents that can do oxidation. But to generalize them, they will just say O in brackets. That is representative of an oxidation. So this is an oxidation reaction because I have increased the number of bonds to a more electronegative atom, in this case, oxygen. But here's another oxidation reaction. Sorry, can you classify this for me? Addition, elimination, or substitution? Elimination. I form a pi bond. This is going to be addition, most likely. This is a reaction that we'll learn. It wouldn't make sense to put O over the arrow because oxygen is not involved at all. But bromine is more electronegative than carbon. I'm increasing the number of bonds to bromine, so I'm increasing the oxidation of my carbons. So this is an oxidation reaction as well. Oxidation does not need to be addition or elimination or substitution. It can be any and all of them. Does that make sense? It's a different perspective, two sides of the same coin. Okay, if it's not oxidation, then it's reduction, again from the perspective of carbon. But what would we say happens with our bonds here? We increase bonds to less electronegative atoms. What's less electronegative than carbon? Hydrogen, boron, metals are all less electronegative than carbon. Once again, we will often write this as, oh, you know what? I'll give you the opposite idea. We'll often write this as H in brackets over the arrow. But much like putting O in brackets over the arrow, it doesn't have to be hydrogen involved in the reaction. We will learn a reaction that involves borane, BH3, which is still a reduction step because I'm adding boron to my carbon. Well, because bromine is a reagent that I'm using here. O is just like a general class. I'll give you another example. If I take that same alkene and I react it with H2, I can add H across it. Why didn't I put H2 in brackets? H2 is the actual chemical. H in brackets is just shorthand for reduction. Exactly. O in brackets, shorthand for oxidation. Okay. And then combination or neither. There's another addition reaction that we will learn that involves hydrogen and boron being added across an not boron, sorry, hydrogen and bromine. We just saw a reaction where bromine oxidized the two carbons because bromine is more electronegative than carbon. And we saw a reaction where hydrogen reduced the carbons because hydrogen is less electronegative than carbon. And now I have one carbon reduced and one carbon oxidized, which means net nothing. This is not considered oxidation, nor is it considered reduction. We can say one carbon was oxidized and one carbon was reduced, but the molecule just went through an addition reaction. Does that make sense? So what I'd like you to do with those same reactions is decide, have the carbons been oxidized, reduced, or neither? And with that, we'll take a 5-minute break, and we'll pick up a little after, quarter after, with some more terminology. This really feels like a different class with how bright it is outside. It's like from up, maybe it's not the same for you guys, but from up there, I feel like I'm here at the wrong time. This is crazy.
Oh, it is. Wait. Well, it's oxygen more electronegative than chlorine.
Good question.
I think it is.
It is. It is more electronegative, but not by much. You know what? I think I gave this to you guys as maybe I lost it.
Trick question.
Do you know what? Carbon and iodine have the same electronegativity. And carbon to bromine, the difference in electronegativity is the same as carbon to hydrogen. So bromine is not that much more electronegative than bromine. So technically it's considered a non-polar bond. I, quite honestly, hate the term non-polar.
Me too.
I think it's misleading. Because chemistry teachers will stand there and say that this is a non-polar bond.
Oh, boron is. Yeah.
So chemistry teachers will say this is non-polar. And then organic chemistry teachers will say the difference in electronegativity here is significant for explaining why BH3 reacts the way that it does, why borane reacts the way it does. It gives us very special, very useful regiochemistry because hydrogen, look at the periodic table, hydrogen is more electronegative than boron by a difference of 0.1. Yeah, so it has a partial negative. Great. But they'll never sit here and say, oh, hydrogen's partial positive compared to carbon, despite the fact that that is a difference of 0.4. Bugs the hell out of me, as you can tell. And I don't get why, I don't get it. I don't know who to ask. Who cares? Yeah, I'll get a lot of people reading it. But in all of my reading and all of my understanding, oh, I'm just kidding. Carbon to bromine is a smaller difference in electronegativity than carbon to hydrogen. But bromine is so much bigger. Yeah, in size. So it's more polarizable, so it can, well, for one, if we say the electrons are held more by bromine, well, bromine's bigger anyways, so they're held there more often. So partial negative makes sense to me. Oh, it's flipped. Okay, so this is this was from my former student, Thomas. He heard me whining and complaining in my OChem 1 class last summer about how, was it last summer or maybe 2 summers ago? About how electronegativity tables never made any sense to me. We're trying to show where electrons are pulled the strongest. And typically, you'll see these tables where fluorine is the tallest because it has the highest electronegativity. But in my brain, that height means that things can roll away from it, not be pulled towards it. I wanted a periodic table that showed how if you placed a marble, an electron like a marble on this periodic table, it will roll towards the most electronegative, the one with the highest affinity, which is fluorine. But in order to show that, fluorine has to be on the bottom left corner, because otherwise in the back right corner, it would be invisible. You wouldn't see the fluorine. You wouldn't see most of those atoms because they'd be tucked away. So I just told him I thought it'd be cool if this, I told my class, I thought it'd be cool if the table showed this as like a gravity sink. And he came back the next day and he's like, here you go. How did you do that? Not at all. No, I don't know that this helped his learning. I didn't assess whether this helped him understand chemistry better. So I only give extra credit when I can see that you have learned something. I don't give extra credit for doing work. That's, you can go get a job if you want to do work. I mean like do your homework if you want to do work. Yeah. What, is that better? Like, that's not a mean thing to say. There's nothing. Why are you laughing? All right. What did you guys say about oxidation reduction? How many of these were oxidation? Let's go through them together. How about this first one where we substitute an alkyl chloride for an alcohol?
Well, that's my reaction.
Okay. Oxidation would mean that I have increased bonds to more electronegative atoms. So I removed a more electronegative atom and substituted it for a more electronegative atom, which means that I have not changed the number of bonds to electronegative atoms. Does that seem fair? So that was neither. It neither oxidized nor reduced the carbon, because remember, this is from the perspective of the carbon. All of these are. The one to the right, where I eliminate the alkyl chloride and form an alkene. Oh, right.
Wait.
The one to the right, the elimination to the right. I reduced a bond to a more electronegative atom, but which means I increased bonds to something less electronegative, which was carbon. But I also removed a hydrogen from the other carbon. So neither. One carbon was reduced. The carbon that lost the chlorine was reduced. But the carbon that lost the hydrogen was oxidized. It was a combination, which cancel each other out. They have a difference in electronegativity. I know. You know, in Gen Chem, the textbook we use introduces nonpolar bonds as pure bonds. They're like, a nonpolar bond is when an atom is bonded to an atom of the same element, which like sets it up for students to think that a nonpolar bond is only O to O, C to C, H to H. And then later they're like, oh yeah, and all of these are nonpolar too, just because they have a small difference in electronegativity. I don't know who made the rules. I just enforce them. And I'm not even happy about that. Here's one thing that I don't want to take up too much of our time, but I do think that it can help you in understanding this a little bit more. We can calculate oxidation numbers. We didn't do that earlier this semester, did we? I think I skipped it because I never have any questions on it. But it's not hard to calculate oxidation state, oxidation numbers. A lot of students will conflate oxidation state, oxidation numbers, with formal charge. We know how to calculate formal charge, I think, pretty well now. Valence electrons minus the dots and bonds around that atom. And it represents excess electrons or deficiency of electrons. Oxidation state is more like comparative. It says this carbon owns most of the electrons that it's around. This carbon doesn't own most of the electrons that it's around. So it helps us say where an atom is more electron deficient and where an atom is more electron rich compared to each other, despite not actually having formal charges. So to calculate this, let's say this central carbon. Here was another question that was missed pretty heavily. Degrees of substitution of carbon. What is the degree of substitution on this carbon? Right, tertiary. 3 degrees of substitution, because it's bonded to 3 carbons. That was a surprisingly big number that missed that on the midterm. Which substitution is missing in vitamin B5? There were no tertiary carbons, but there was a quaternary, couple of secondaries, and a couple of primaries. A few primaries, actually, but no tertiaries. All right. In order to calculate this, I will give a +1 to carbon for every bond that it steals electrons from. And I will give a -1 to carbon. No, I said that wrong, sorry. Start over. +1 to carbon for every bond that it loses electrons to. That's why it gets a +1. It has lost electrons for every bond to something more electronegative. A -1 to carbon for every bond that it steals electrons from. A -1 for every bond to something less electronegative. And if it's bonded to carbon, 0. Not positive or negative. So this carbon is bonded to carbon, 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 0, and chlorine. So this carbon is a +1 oxidation state. Out of its 4 bonds, it loses electrons in one of them. This carbon is bonded to carbon once, 0 oxidation state, and hydrogen 3 times, which it steals hydrogens from. Sorry, it steals electrons from. So -1, -2, -3 oxidation state. Tracking with that? True, it's a nonpolar bond by definition, by human definition, but it is still more electronegative, so it gets the electron density from all of them. So I have a +1 carbon and a -3 carbon, and my product took me to an alkene What is the oxidation state now of the carbon on the bottom? Zero. And the oxidation state of the carbon on the top? -2. What change happened to this carbon? Did its oxidation number become more positive or more negative? More negative. So did it gain electrons or lose electrons? It must have gained electrons by becoming more negative. Is that oxidation or reduction? Yeah, we have to go back to that old mnemonic. Oil rig, or Leo the tiger says grr. Any others that you guys have? Yeah, oil rig is the one I like. Oxidation is loss of electrons. Reduction is gain of electrons. So this is reduction. What happened to my other carbon? More positive or more negative? More positive. Went from -3 to -2. Is that gaining electrons or losing electrons? That's losing electrons. If it went more positive, that's oxidation. So one carbon has been oxidized, one carbon has been reduced. Overall, nothing has happened to the molecule. It's neither been oxidized nor reduced. All right, what about down below on the left? I've got this addition to a primary alcohol. Feel all those gears turning now. That carbon on top has definitely been oxidized because it gained a bond to a more electronegative atom. But the center carbon, the tertiary carbon, gained a bond to a less electronegative atom. Neither. How about to the right? Br2 and methanol across the alkene. Both atoms gain a bond to a more electronegative atom. So both atoms are oxidized. How about to the left, carbonyl to an alcohol? Sorry. We had neither oxidation. Now on the bottom left, I've got carbonyl to an alcohol. Reduction. Do you know the oxygen is neither reduced nor oxidized? The oxygen had 2 bonds to carbon, -2, because it steals electrons from carbon. And then it has 1 bond to carbon, 1 bond to oxygen, -2, because it steals electrons from both. So we're not paying attention to the oxygen. This is all the perspective of the carbon. But increased bonds to hydrogen, reduced. How about to the right, where I take an alcohol and I form an aldehyde? Oxidation. Please. Okay. Okay, going backwards is actually a huge thing. I get this all the time in the second half of the class, where a student is given a question to answer and they describe the product going backwards across the reaction to the reactants. So I'm glad you pointed that out. That you're not alone. Keep your eye on that. To the right, did we say this already? Alcohol to aldehyde, oxidation. Alkyne to alkene. More hydrogens on both carbons. Reduction. The other ones are maybe a little challenging. No, not really. To the left, reduction. The carbonyl carbon now is bonded to another carbon, so it has lost bonds to less electronegative things. The carbon on the right has lost its bond to bromine, so they've both been reduced. On the right, both carbons bond to things more electronegative, so they've both been oxidized. So a few things I want to point out about chemical reactions. You're looking at a lot of them here, but this is really just a small sampling. Already, there's a few things that we can see showing up over the reaction arrow. Okay, I guess I want to pull back. You know what? I really think teaching OChem, I'm at a disadvantage for not teaching Gen Chem 2. When I started teaching Gen Chem 1, I started realizing all the things that you barely get a glimpse of before you get into OChem. So I started leaning into teaching those a little bit better in my OChem classes. And I wish I could see what exposure you've had to reactions in Gen Chem 2. Have you ever seen a reaction where the arrow helped present reagents, or are you used to seeing reactions that show you chemicals on one side, chemicals on the other side? Organic chemists don't always like to show all of their chemicals here. For instance, there's no reason that first reaction couldn't be drawn like this. And you know what I didn't give you on these? I didn't give you the byproducts either. There's no reason it couldn't be drawn like this, but no organic chemist will draw it like this. Instead, we like to identify the major organic reagent, and we describe this as our substrate. I had a student once that asked, why do we call it substrate? Because in his biology application, substrate was, actually, I don't know, what the thing of interest ate or what it sat in, but the substrate was not the thing of interest. And in organic chemistry, the substrate is the compound of interest. The things that we'll react the substrate with, we can take up less space by just showing those over the reaction arrow. I mean, we're going to have a reaction arrow there anyways. So by putting it over the arrow, we just save a little bit of space. But writing it this way, there is literally no difference between writing it this way. It's just a matter of preference and what you might be aiming to communicate. The arrow itself has no meaning above or below, but there are a few things that people will try to communicate above and below. Sometimes we will communicate a reagent that the substrate is reacting with over the arrow above it, and a solvent that helps mediate the reaction, keep things afloat, keep things dissolved, provide heat for things to ram into each other. And we'll represent that under the arrow, but this is not always consistent. Sometimes we don't even put the solvent. There's a lot of reactions on this sheet that require a solvent. No solvent has been named. There are some reagents on here that are the solvent, and we call those reactions solvolysis because the reaction itself is with the solvent. The solvent is a reactant. Kirsten?
Question that's not really related to this actually, but back to the last three bottom three things.
Oh, can you
Go over.
hold it on just for a little bit, because I'm gonna get back to those too, and then maybe you're.
Go back over whether they're addition or
Oh no, but I will come back to them, and
That's the main thing.
I think it might make more sense. I think it might make more sense when we do get down to that one. Sometimes this reaction arrow allows us to show multi-step synthesis, in which case the arrow often serves above the arrow. We'll put the first step, and below the arrow, we'll just list all of the other steps. This allows us to communicate a number of transformations to our substrate without showing everything that comes up in between. Sometimes we call this multi-step synthesis. Sometimes one step requires two actual steps. So you guys see this where you've got first BH3, then basic aqueous hydrogen peroxide. We consider that a one step. That's one reaction that we're going to learn. But it itself needs to be done at two separate times. You take the substrate and first react it with borane. And when that reaction is done, you mix in the basic aqueous hydrogen peroxide. Or this reduction of the carbonyl to the alcohol. First, you need a reducing agent, lithium aluminum hydride, before you provide an acid workup. And so those 1, 2 labels just help us differentiate. These don't happen at the same time. When you go into the lab, if you dump all of this in at once, it will explode on you. Or at the very least, your substrate will not go through the change you want. They have to be done in that sequence. Towards the end of the semester, though, we're going to show how I can take several of these reactions and kind of run them in sequence. Take, for example, the top right, where I have an alkyl halide transform into an alkene. And then I have that same alkene go through a reaction to become a primary alcohol. If that alkene is not something I'm going to end up with, if it's not my main target molecule, then I might just show the alkyl halide, all of the steps needed in between, and then the primary alcohol that I get at the end. So our multi-step synthesis is something that you'll see, and we'll use that reaction arrow again. Most of these, and this is me coming back to those ones at the bottom, most of these are intermolecular reactions. I've got a main substrate, I introduce some other reagent, and those two molecules interact with each other. These are very common. But we will also see some intramolecular reactions. And again, we're just drawing lines in the sand. Some of these are a little more complex. They involve 2 or more reagents. But at some point, an intramolecular reaction has the substrate react with itself. And this, I think, Kirsten, is where it becomes challenging to describe them as just one thing. Why did I look at Jordan when I answered Kirsten? 1 carbon down here. So if we look at that bottom left, I'll draw it up here as well. If we look at that bottom left reaction, 1 carbon down here. Actually, I forgot to mention this needs to be 2 steps. The magnesium comes before an acid workup. 1 carbon substitutes. It has a bond to bromine, and in the product, it has a bond to carbon. It has gone through a substitution reaction. The other carbon has gone through addition. It had a pi bond. That pi bond was consumed. 2 things happened at the same time. So it's not clean cut as just one or the other. That's a little bit more common with intramolecular reactions. You've got different parts of your substrate interacting with each other, which means different things might be happening for each of those carbons. In this case, they both happen to be reduced, but they reacted with each other through different reaction types. One was a substitution reaction for one carbon. One was an addition reaction for the other carbon. And on the right, we see something similar. Both carbons are going through oxidation. Both carbons are going through addition, but the alcohol on the right seems to be going through a substitution reaction. The alcohol goes from OH, alcohol, to OR, ether. So there's both substitution and addition happening because of that intramolecular reaction type. Yes, and not one that I would put on an exam question for you to classify. Although in my head, I saw them both as being addition reactions. I didn't anticipate visualizing either of them as substitution. That's the beauty of the student.
When you say you visualize that as addition, are you just kind of like, because when I also listen to that, well, for the love of it, but
Yeah.
I just see the background,
Yeah. It's good. And the reaction on the left is literally called acyl addition. And the reaction on the right is called alkene addition. But because they're intramolecular, there's also a part of that molecule that's going through substitution. So it is more complex because of its intramolecular reactivity. These terms make sense, correct? Inter and intra. The difference between intermolecular forces and intramolecular forces is hydrogen bonding intermolecular versus covalent bonding intramolecular. Some students don't like this idea that molecules can wrap around and attack themselves, but molecules are a lot more like shoestrings than they are spaghetti noodles. They are floppy. And we've looked at all of those conformational rotations that molecules can go through. So when you've got a long chain like that, that chain gets bumped around by other molecules until it wraps around and hits itself. It's actually much easier for a molecule to react with itself than it is to react with another molecule if it's got the capacity for it, if it has the capacity to react with itself. It takes less time because all it has to do is loop around. To react with another molecule, your molecule must first swim through billions of molecules of solvent and find another molecule to react with. Unless your molecule is the solvent, in which case, then it will happen very quickly because there's a lot of solvent around all the time. All right, we've got 8 minutes. So let's just talk about some of this terminology. We've talked about this already, regiochemistry and stereochemistry. Somebody give me the review of what this means. Left, right. Okay, maybe. Yeah, the region around a reactivity, a region around a part, the parts of it. Can you think of like what things we've talked about that fell under the umbrella of regiochemistry? Degrees of substitution, primary, secondary, tertiary, quaternary carbons. That's part of its regiochemistry. Functional groups. Technically regiochemistry, what's around it. And what about stereochemistry? Spatial arrangement. And what things have we already talked about that fell under that umbrella? Cis-trans in the di-substituted chairs. Cis-trans groups. Chiral carbons and their absolute configurations, R and S. Newman projections, eclipsed conformation, staggered conformations. Those are stereochemistry. Our regiochemistry terms come first on that little list. Markovnikov, I will shit on him all semester. He described a rule with addition reactions. He said that hydrogen adds to the carbon with more hydrogen. That's a regiochemistry term. Hydrogen adds to the less substituted carbon. It's a dumb rule because it insinuates that hydrogen is drawn to that carbon maybe because of other hydrogens. It has nothing to do with the hydrogen. And there are a lot of addition reactions that don't involve hydrogen. So his rule can't even be applied to a lot of different stuff. We also have an anti-Markovnikov. No, it was him. The anti-Markovnikov rule says H adds to the more substituted carbon. What good is a rule if you have to have the opposite of your rule? And again, if hydrogen's not involved in the addition, these rules don't even apply, which is not great because there are a lot of addition reactions that don't involve hydrogen. I made a mistake though. On here, I put Markovnikov, Hoffman, Zaitsev, and anti-Zaitsev. I should have put Markovnikov and anti-Markovnikov, Zaitsev, and Hoffman. So that is just another thing for me to fix down the road. Zaitsev developed a rule about elimination reactions. His rule is that the most favorable alkene will form. We're going to cover this later in this, well, I guess in Unit 7. This basically says the most substituted alkene prefers to form. We haven't actually talked about degrees of substitution with alkenes, but I think you can imagine it involves degrees of substitution for the carbons. A more substituted carbon will lead to a more substituted alkene. Anti-Zaitsev is actually what we call Hoffman. And Hoffman's rule is that the least substituted alkene forms. So we will look at certain reagents that react with a compound to give a Zaitsev elimination and form a more substituted alkene. And we'll look at reagents that give Hoffman elimination, anti-Zaitsev elimination, a less substituted alkene. So these terms help us describe the regiochemistry of our reactions. And they're all named after dead guys. Go figure. Our stereochemistry didn't get any dead guy names. Our stereochemistry helps us describe how groups are arranged relative to each other after a chemical reaction. We've got syn addition. Syn here is synonymous to cis. So when we say syn addition, we say that two things have added to the same face. Oftentimes that's of alkenes, the same face of an alkene. But sometimes that translates to the same face of a ring. Anti-addition then is just the opposite. Groups add to opposite faces. The last term that we'll see throughout the rest of the semester to describe stereochemistry is anti-periplanar. And to be honest, I'm realizing in this moment, this should have come up when we did our Newman conformation unit, because this is best identified from a Newman projection when we talk about this anti-periplanar, we're talking about elimination. And we need to have a hydrogen that is anti and in the same plane to a leaving group. And that orientation is really well identified from our Newman projection. They're just directly anti to each other. Where they came up with this term periplanar, I don't understand it actually. So honestly, it just could be called anti-elimination or anti-planar. But by being anti on a Newman projection, they're already in the same plane. So I feel like this idea of periplanar just is a little bit redundant. When we come back on Wednesday, we'll talk about some solvents and we'll classify them. The thing is, I'm not going to have you work a lot with solvents, but I do want you to be familiar with some of them. So when you see them come up in your homework, you know what you're looking at. Then we're going to talk about the big thing about chemical reactions. Reaction coordinate diagrams. How is energy required throughout a chemical process? And the components within it, like transition states, reactive intermediates. And then we'll have a brief intro into mechanisms where we talk about how those bonds form, how those bonds break in order for a chemical process to proceed. Thank you guys for your time. I'll see you Wednesday.